really apologize. Today we were supposed to discuss start a new topic. However, I thought that since your exam is also nearing, and I'm yet to announce the exam date, but most likely it will be on Wednesday, November 6th. Can you please guys check whether November 6th is Wednesday?
Yes.
It's Wednesday? Yes. Okay. So I'll make an announcement today, but here it is. Midterm exam
So it's going to be online Wednesday weekend.
So please take a note that the exam time will be first time, and the syllabus would be electrostatics. However, whatever we discussed in mid-exam 1, that won't be included in your second exam. So whatever we covered after midterm exam will be the syllabus for the next exam. And the structure of the exam would be theory and math, approximately half of half, right? So as the exam is near, and I thought that instead of starting something new, maybe I spent a few class on reviewing what we discussed so far, so that it helps you to understand a little bit more and help you to get better prepared. So let us see what we have discussed after midterm exam 1. We discussed about the idea of resistance. We also discussed about the idea of capacitance, and we did some experiments as well. So I guess the syllabus is not too horrific. Like, it's pretty much known to you, all of you guys, especially since you have taken a course on physics. They discuss the basic things of it. However, pay special attention because I think I discussed a lot of stuff which might not be there in the book, which is very important for you to know. So take a look at the YouTube video that I posted, and also talk to your peers, so to see if you have missed anything. So in order to review, let me ask you one question. In the class, I described that resistance R is equal to L divided by sigma A, where L is the length of the wire, sigma is the conductivity, and area A is the cross-section area of wire. And sigma is conductivity. So in one of your exams, class quiz exam, I asked you guys to answer one question where it looks like the following. I gave you a picture of a integrated chip. So integrated chip In an integrated chip, we have a silicon device at the very bottom. So these are all silicon devices. And on top of silicon device, we make wire by depositing copper metal. So these are copper metals on top of silicon, and these are the silicon device. That will act as a transistor. So the typical size of a copper pillar is in the order of micrometer. Let us say 1 micron. Whereas the size of silicon device is, well, let's say 50 nanometers. Alright. So let us say that we have some pads on top of it. We apply voltage. These are also made of copper or sometimes lead or some kind of alloy of metals. So in the exam, I asked you the following question. I say that let us say we apply a voltage V like this on those two copper pads. So we expect that because of applying voltage, we have some current that will go through the copper pillar and come out of the other side, right? So this is how we have any. So if I apply voltage, current is most likely go through this route. So one of the design criteria of why people engineer IC is they try to minimize the resistance of the current path. So since we know that resistance is related to the length of the wire and inversely proportional to the area of the wire, we always try to minimize the length and maximize the area in order to reduce the resistance. So in case of an IC where we have copper wire, we know that the copper wire has a high conductivity, goes up to 10 to the power 7 Siemens per meter, and silicon device has a very moderate conductivity, just 1 Siemens or 2 Siemens per meter. So in order to have your resistance as minimum as possible, how are you going to design this IC? First of all, let me ask you this, that the copper, how exactly you want to design these things? Do you want to design it to be very wide or very narrow, very tall or very short? How do you want to design it in order to minimize the resistance?
Wide and short.
So it should be short and it should be narrow?
Bigger.
Wide. So the copper wire, the copper pillar should be short and wide. All right. So, why don't we make it as short as possible, or why don't we make it as wide as possible? Let me answer this question first. Why don't we make it as wide as possible? What's stopping us? What is the physical bit? Go ahead.
Make it too close, could be discharged into too wide.
Absolutely, yes. And also, you don't have infinite space inside, right? So typically, your size of the device is 1 centimeter. And you have to make sure that inside that 1 centimeter size, you are going to pack as many devices as possible. Okay? Why as many devices? Because the more the device, the more its computing ability. So, if you want your computer to work very fast, you need to have a lot of devices. You need to have a lot of transistors. So that's one problem, that why we cannot make those copper pillars arbitrarily wide, because they will clash to each other, right? And if those copper pillars come very close to each other, they might discharge through it. So that's very good that we cannot make it arbitrarily wide, because cannot be too wide, else they will discharge to themselves. All right. Now the next question, I understood that we cannot make it arbitrarily wide. How about its length? You said that copper pillar should be as short as possible to minimize resistance. Why can't I make it as short as possible? Like the shortest possible thing is probably take the copper pad to be very close to the silicon device and just eliminate all these copper pillars. Why can't we do that? What stops us from doing this? This is a little bit more tricky, but can you think of it? The clue is, I say that in order to improve your IC performance, you have to pack as many silicon devices as possible. Okay? Does it give you any clue? That why can't I make this copper pad take it as close as possible to silicon device? First of all, let me ask you this. If I have another IC where I have silicon device, and on top of silicon device we have copper pad. Between this guy and this guy, which one will have less resistance? This guy. Everyone understands that, right? This guy has this resistance. But why don't I divide it like this? What's wrong? Very good. So why copper pad has to be bigger? Why can't I make it smaller? You told it just a moment ago. Why can't I make it very small? So she's saying that copper pads are much bigger compared to the silicon device. The silicon device is 50 nanometer. Copper pad is probably 1 micrometer. Okay. So of course, if you want to bring them close, you have to match their size. And the question is, why can't I match their size? What's wrong if I just make it smaller? You see it? More resistance, right? This is more resistance. So you have to make it wide. If you make it very small, your resistance is going to go up, right? And also, remember that if you make it very small, they are more likely to fail. So failure is one thing which you need to take care of, that you cannot make things arbitrarily small, and you cannot make things arbitrarily small because the resistance is also going to go up. So two things. One, your copper pillar cannot be arbitrarily short, otherwise this size has to be reduced down, which makes a problem, resistance goes up. So in order to match the size, we make the silicon device small, but then gradually taper it out so that the size matches with the copper pad and the silicon device. So you understood why it has to be wide and why it has to be short, but it cannot be too wide because then it will discharge, and it cannot be too short because then Your copper pad has to be very short to match size. Cannot be too short, else size will mismatch. Is it a false alarm or true alarm? Could we just run away?
Just a quick question. You might not know off the top of your head, but do you know what chapters in our textbook would correspond with this material?
This one?
Yeah.
Unfortunately, I don't think it
Okay.
So
Not this specifically, but just resistance capacitance.
Oh yes, resistance, definitely.
Yeah.
It is there. So I think if you look at Ulabi's book, Fawaz Ulabi's book, it should be there in chapter 4. Give me
Okay.
just 1 second.
Thank you.
So in Fawaz Ulabi's book, chapter 4 discuss about resistance and capacitance. Okay, but these kind how the resistance, the idea of resistance is implemented in IC design, that might not be there. Okay. Yes, you had a question.
Can you explain why that they can't mismatch like their size?
So if you make it too small, then it's going to increase the resistance, right? You cannot make it too small. It has to be wide. And also,
Make what too small?
oh, so we are discussing the following. We say that the copper pillar, in order to make the resistance small, you have to bring them down. That means you have to take this copper pad and just put it on top of the silicon device, right? Now the silicon device, they are actually very, very small. So using that 1 centimeter by 1 centimeter space, the number of silicon devices is actually 1 billion. Okay. So this means in order to fit the size of the silicon, your copper pillar, the pad of this copper has to be very, very shrunk down. If you make this copper pad very wide, and each of these copper pad has a size of 1 micron. Can you put a 1 micron cap on a 50 nanometer silicon device? Remember, 1 micron is 1000 nanometer, right? And this is very small, so you cannot put a big cap on the small die.
Why can't you? Like, is there any?
So let us say that we have the IC, and we have a silicon device. Let us say all this silicon device is arranged like following. And we have 1 centimeter space in total. Each of these silicon device is 50 nanometers. Right? So if I have to put in this copper pad on top of these other die, can I make it 1 micrometer? Do I have space to make it 1 micrometer? So let's say that I want to make copper pads on all of these devices. Can I make it? Let's say I make 1 micrometer device. So that's pretty much touches the other die. Right? So you understand that you cannot put this 1 micron device, 1 micron pad on top of something which is just 50 nanometers. You don't have the space. So this is why we know that we have to make connections with all of the silicon devices. So the other possible way is that instead of just putting the cap on all these silicon devices directly, you create some jumper wires. So maybe you have wires which are connected at many different levels. So maybe these two guys will be connected at one level, and maybe these two guys will be connected at another level. So by doing layer of copper wires, by doing the layer of metals, you can make the connections with all the silicon devices. But if you try to connect all the silicon devices exactly at the very proximity, you cannot do it. You don't have the space. Does it answer your question? It might be clearer once you take some courses on IC design. So for now, I think it's okay if you just look at the size mismatch and try to understand that why.
So would there be losses in current if they don't exactly match up?
Say it one more time.
Would there be losses in current if they don't match up perfectly?
You cannot connect it simply. It's not about the loss. Think about it one more time. Maybe I'm not explaining it in proper way. So you have, in 1 centimeter space, you have 50 nanometer device. How many 50 nanometer device you can add up here? You just divide 1 centimeter by 50 nanometers, right? So let us just do the math. 1 centimeter means how many nanometers?
7, right?
10 to the power 7?
Right, yeah. Because centimeters 10 to the negative 2, right? And then nanometers.
And then you divide them by 50 nanometers. So it's a big number, right? So in order to bring the cap on this silicon device, each of these copper fillers, each of these copper cap also has to be 50 nanometers. Do you agree on this?
I understand. I'm just like, why does it have to be the same size? Like, what reason? I understand you say like, yeah, it's bigger than the silicone, so you can't put it on there.
Mm-hmm.
Why can't it overlap? Like, I can put my binder on my pencil; it's on the same size. Like,
Understood. So let's say, so let us say that you can take a big metal. This is a big metal, and you put it on top of the silicon device. But it's overlapping the other silicon device. Then these two silicon devices are not different. You're saying, right? Let's look at here. Let's say that I make this copper pad so big that they touch each other. Will the current go through this part, or will the current just go through here? The current will just go through here, right? So you cannot make this copper pad so large that they start to bump into each other. Then there is no point of applying any voltage. The silicon device underneath, they will not see the voltage. They will just go through, right? So this is why you can definitely, if you have just one device, you can connect with the copper bump. But if you have many devices, you cannot put all these big copper bumps on each of these individual silicon device while also keeping them isolated from each other. Does it answer your question? No. Thank you. Like, this is really good. This is really good that you actually you keep me pushing until you get to the satisfactory answer, which is really good. Really good. I appreciate it. So don't bother. Just like what Logan did, I want you, all of you, to follow the same strategy. Unless you are satisfied, keep pushing. Keep pushing your teacher. Did you get your answer or not? Okay, good. Because remember that, like, your teacher is the only right source that can give you an answer. The book may not give the right answer. So take the maximum benefit of it. Thank you so much. Anybody has more questions on it? No. Any questions? Alright, so we discussed that copper pillar has to be short and wide, but it cannot be too wide as they will touch each other. It cannot be too short because then there will be size mismatch. Alright. So how about the following? Let us say that we design an IC let us say we design an IC which looks like this. The IC at the very bottom, we have silicon device, and then it is connected by some copper pillar. These are the copper pillars. And then we have copper bump. So another guy, another engineer, they designed the following. They say that, how about I make this? At the very bottom, I take silicon device, so I make big silicon device. and then on top of it I put copper bump and copper pillar. These are all metal layers. Diameters are the same. Let's say this is also 1 centimeter, and this is also 1 centimeter. Their height is also same, which is 1 micron. The only difference between these two guys, let's say design A and design B. So design A and design. The only difference between design A and design B is that design B has bigger silicon device. So these silicon devices are wider. So let's say this guy was 50 nanometer. Maybe this guy is just 100 nanometer. Twice bigger than the previous one. Which one will give you better performance in terms of resistance? So if I ask you that which design will give you least resistance, what would be your choice? The design A or design B? Design A. Why? Why do you think the design A is giving you least resistance compared to design B? What is your argument?
There's less length through the silicon devices.
Yes. So remember that resistance is proportional to length and inversely proportional to area. So whenever we look into minimizing resistance, we have to always consider the path of the current. So the path of the current is the following. It goes straight downwards to the copper pillar, and then it goes horizontally from one silicon device to the other silicon device, and then again it becomes vertical, go upward and come back. So when the current goes through vertically, we want to make sure that the path is as wide as possible. That's why we make this copper pad and also copper pillar very wide. But when it reaches the very bottom, now it changes the direction. So instead of going vertically, now it goes laterally. Right? It goes laterally. If it goes laterally, we must want to make sure that the length of the path is as small as possible. Right? If the path has to be very small, then the silicon device has to be very small. Okay? So this is why if you can reduce the length, the resistance is going to reduce. Also remember that silicon device has a much less conductivity compared to copper. So copper has 10 to the power 7 Siemens per meter conductivity. Silicon has just 1 Siemens per meter conductivity. So there is a big margin between the conductivity of copper and conductivity of silicon. So since the conductivity is very small, in order to make it up, you need to make the length very, very small. Do you see the point here? If your conductivity is very small, then the resistance is going to go up for sure, right? Now how you are going to reduce resistance? You have two more parameters in your hand. One is your length, the other is your area. So if you make the area very wide, it can cover up for the conductivity. If you make your length very short, it can also cover up for your conductivity. Now, if you make the area very wide, that's also one option. The silicon device could be very, very wide. That's also one possibility, right? We can make the silicon device very wide, so it has two dimensions, 1 centimeter in these dimensions, and the other centimeter inside the direction of the board, into the plane of the board, right? So we can make the silicon device very wide so that it has less conductivity, it has less resistance. But the problem is, if you make it very wide, you won't have enough space to put more silicon devices. And remember that always your chip processors depends, the performance of the processor depends on how many silicon devices are there.
When you say area, is it the cross-section area? Right, not the actual area of the wire itself. Just the where it's coming in.
So if the current goes in these directions, we always look at the cross section.
Okay.
So like cross section of my hand.
Yeah.
So in a similar way, in order to reduce the resistance, we have two options for silicon device. One, we can make it very big, very wide into the plane of the board, but that makes the number of silicon devices to be very small. We want to make silicon device as much as possible inside this IC. So the other option is that you make the silicon device very short. If you make them very short, then the length would go short and the resistance would become minimum. Understand? So I think this is one question which probably many of you guys missed in the exam, which is okay. I mean, you are just learning this stuff. So here is again one more time that we are trying to minimize the resistance of the entire IC system, and that's why we have to make sure that each of these devices will have as minimum resistance as possible. So whenever current goes to the copper pillar, you want to make this copper pillar very short, very wide. You have to make this silicon device very small, so that the eventual resistance becomes minimum.
So, in like the chip industry, when they say something is made on a 3 nanometer process, is that 3 nanometers the width of the silicon inside?
Very good question. So, Sudharshan asked a very interesting question. He said that in today's world, you might see that the chip industry, they advertise that we develop 10 nanometer node, we develop 3 nanometer node, or even further down. Have you heard of this term? Like 3 nanometer, 5 nanometer? Never? It's okay. So what they're saying is that they are able to design a device which is very, very small. So the smaller device is very difficult to make, but the smaller the device, the better its integrity. So you can pack more silicon device inside the IC, the smaller it becomes. So at one point of time, the process node actually corresponds to the physical side of it. For instance, long time back when we started just designing the IC, we say that it's 1 micron node. So 1 micron really meant that it's 1 micron device. Silicon device itself is 1 micron. And then it went up to, from 1 micron, we go up to 500 nanometer, then probably we go to 180 nanometer, then 65 nanometer, then 32 nanometer, 22 nanometer. So each time, like every year or every 2 years, we shrunk down the chip.
Yeah.
Okay. However, we only maintained the actual physical size versus what we say about the process node 1:1 until we reached to 45 nanometer. And it's a tale about like almost 1 decade ago, in 2010, early 2010. At that time, we said that our process node was 45 nanometer. Then we indeed mean that the chip itself is 45 nanometer. The silicon device is 45 nanometer. However, then people realize that they cannot make it any shorter. There are other physics that involves it. It becomes very difficult. And one of the problems is that not only physics, but also the problem is if you make them very short, it takes too much to just manufacture them. So cost increases drastically. So just imagine that if I can make it short, but if my production cost increases too much, you cannot buy it. Like only the most rich people will buy it. These people are stupid, so they won't do anything with these computers. So the point is that it's not only about making it shrunk down, it's also about how to shrink it down without increasing the cost. So people understood that after 45 nanometer, you cannot actually shrink down the actual device size. So people improved the device performance by some other ways, like doing an improvement in the system, not in the chip itself, not in the device itself. But people realize that if they always stick to the same value, like 45 nanometer, then nobody will buy it. So every time, you have to marketize this stuff. Right? Yeah. So they kept on saying that, okay, this time it is 22 nanometer, this time it is 10 nanometer, but actually it's 45 nanometer. Okay. It's no more increasing anymore.
Interesting. Okay.
Sorry, I think I diverged a little bit.
Yeah.
But what we discussed here is that the process node, that semiconductor chip often advertised, it was supposed to relate with the actual physical size of the chip. but which is not true in these days. All right, so coming back to our discussion, that in order to minimize the resistance, you have to just play with this length and the area. For the silicon device, in order to pack the silicon device as much as possible into the IC, and in order to make the resistance as small as possible, you make the silicon device very small. Okay? So this is the reason why everybody is trying to slim down the silicon size, because they want to minimize the resistance. Okay? And at the same time, you can decrease the resistance by increasing the area. So we do not increase the area of the silicon device, but we increase the area of the copper coil. Okay? So please remember in mind that how the design has to be decided based on their resistance. Okay, so this is one thing that I wanted to discuss. And the other thing that I wanted to touch base a little bit is the idea of capacitance. So for capacitance, we know that capacitance is related to the geometry like the following way. So capacitance is equal to, for a parallel plate capacitance, C is equal to PA over D for parallel plate capacitance. So we have two different metal plates and we bring them close to each other, and the area of the plate and the distance of the plate is D, area of the plate is A, and the medium inside those inside those metallic plates are epsilon. Then the capacitance of the parallel plate structure will be defined as epsilon A over D. If you take air medium, then the epsilon of the medium is just epsilon of air medium is simply 8.85 10 inverse farad per meter. For other material, for instance silicon material, I think it was 12 times higher than air medium epsilon. So we discussed that if you take, if you consider the energy which is stored inside this copper capacitor, then it is supposed to be half of CG square. Right? So this is the energy which is stored inside the capacitor. Energy stored in capacitor is half CG square. So we discussed that any natural medium, any natural phenomena always want to minimize their energy. So that, for instance, if you think about a mechanical system, let us say we talk about a hill and a valley. Then at the peak of the hill, if you place a ball, the ball is supposed to roll over all the way to the bottom, because at the very bottom, the ball will have minimum energy, minimum potential energy. So in case of the mechanical object, the potential energy is proportional to mgh, and they always want to minimize the potential energy. And the only possible way of minimizing potential energy is to reduce the height. That means the height from the ground. In the same way, in a capacitor, the energy stored in a capacitor is half CV square. And if the capacitor plates can move around, they will always reorganize in such a way so that the total energy inside the capacitor minimizes. So let us say that our capacitor plates are not fixed. They can move around a little bit. So if I bring some charges, let's say this is positive charge and the other plate is negative charge. In this condition, how these plates are going to move around? Are they going to come closer to each other, or are they going to go further away from each other? That was the question. So let's look at the structure one more time. Both of these plates are connected to a voltage. My question was that if the voltage induces a positive charge in one metal plate and negative charge in another metal plate, then how these guys are going to move around? Are they going to come close or go far apart? So in order to understand that, always look at the energy stored and apply the principle that these guys will move to a new configuration where the energy storage will be minimum. So we can go ahead and further rewrite the capacitor in terms of its area and the distance between the capacitor, distance between the conductor metal plates, to get to the following answer, that energy stored W is equal to half epsilon A over D multiplied by V square. So this tells you immediately that in order to reduce your energy, you must increase the distance between the copper plates. So if you connect these voltages across these copper plates, in order to reduce the energy, these copper plates, if they can move around, they will go further away from each other. Alright? Now that might sound a little counterintuitive. Does it sound counterintuitive to any of you guys? That if I have two metal plates, one positive and one negative, should they come closer or should they go away from each other?
You think closer?
You think it's closer, right? Why do you think it's closer? All right, spell it out.
Positive and negative attract.
Right. So which law of physics governs that? Coulomb's law. Just Coulomb's, right? If you take two charges, positive charge and negative charge, they're supposed to come as close as possible to each other. But here we learn something new. It says that energy stored in a capacitor is half CV square, and energy is inversely proportional to the distance between copper plates. So in order to reduce the energy, we have to increase the distance. So of course there is a contradiction. It doesn't match with the common sense. What is going on here? Let me write the energy expression in a different way. Energy can also be written in the following way. Energy is equal to W is equal to half of Q square by C, where Q is the charge. Q is the charge of the conductors and C is the capacitor. Okay. Q is the charge of the conductor and C is the capacitor. And these two equations are exactly same to each other. Let's look at this. Q is equal to half C. Q is equal to CV. Charge is equal to capacitance multiplied by the voltage. So if you place Q equal to CV in these equations, you will get W is equal to half CV square. Do you follow this? These two equations are exactly the same. Any question up to this point? No. Okay. Now let's just plug in the value of capacitance into this equation. How should I write it? At the numerator I should write Q square, and the denominator I should write epsilon A divided by D. Isn't it? Are you following this?
Yeah.
So I got two different expressions. W is equal to half CV square. W is equal to half of Q square by C. Both are same expression, because if you just plug in the value of Q as CV, you will get to the other value. So they are same equations. And then I plug in the value of capacitance, I get to the following expression. W is equal to half of Q square D by epsilon A. So if I want to minimize the energy, should I reduce the distance or should I increase the distance? Reduce. How come they are so different? Like one says that you have to increase the D in order to minimize energy. The other guy says that you have to decrease D in order to minimize W. They are same thing. I'm not cheating. I just use the same formula, Q equal to CV, to get to the, but I'm getting completely two different results. Right? What is going on here? Did I mess up somewhere?
The amount of charge can change.
Go ahead. Spell it out further.
The amount of charge can change.
Mm-hmm. Keep going. Yeah, you're on the right track.
That's all I had.
So you're saying that the amount of charge is going to change. Okay? Go ahead. Go further. So you are saying that if distance changes, maybe Q is also going to change. Is that what you're saying?
Yes.
Okay. How about here? I say that if distance decreases, the energy is going to reduce. Does decrease of distance to change V? Yes. It would. Think about this structure one more time. We have copper plates connected by wires to a battery. The battery has a particular voltage. Let's say it's 5 volt battery. So in this scenario, do we expect that if I change the distance between two copper plates, will the voltage change? No.
The 5 voltage will change.
Pardon?
The 5 voltage will change. But
So these are copper wires. These are very good conductors. Consider that these are ideal conductors. That means it has zero resistance. If they have zero resistance, that means all the voltage must be dropped across the copper plates. Because there is no other place where the voltage will be dropped. These have zero resistance, so no voltage drops across the copper wires. No voltage drops across these other copper wires. So the only way we can drop the voltage is those copper plates. So all this 5 volts is going to appear across this distance D. Okay? So the amount of the voltage of the battery and the amount of voltage that appears across these copper plates are exactly the same, given that these are very good conductors. Alright? So in this scenario, even if I change D, the voltage is not going to change. Right? Everyone follows. How about this guy? If I increase the distance D, is Q is going to remain same? Look at that. Q is equal to CV. Right? So if distance D increases, is Q going to remain same in this formula?
Yeah.
So voltage is going to remain same. How about C? C would go down actually, right? So C is equal to FC is equal to epsilon A over D. Right? So if I change D, Q square is going to reduce because it changes capacitance. So the point where we were making some contradictions is that we were not considering that when one parameter changes, whether it also impacts the other parameter or not. In this situation, where we have voltage connected across these two copper plates, the voltage is always going to remain fixed. What may change is the charge. Okay? So this is why when you use the energy expression, I prefer using this expression. Because in this expression, the voltage is going to remain fixed. So I can only consider the other factors. In this expression, you can also use this expression, but be very careful. In this expression, we have Q square, and you have D. If you change D, Q is also going to change. So don't rely on this expression. And if you rely, it's okay, you have to just again take care of the fact that Q is going to change, because Q is Cd, and C is equal to epsilon A over D. So Q is also going to change. If you take care of that, then probably you will reach the same answer. That yes, increasing of D would reduce the energy. Okay. So in the first case, when we kept the battery, because of the battery, the voltage across this copper plate is always going to be fixed. So under such conditions, we will always have the distance D increasing. But if it was the other way, let's say that instead of having a constant voltage, if we always apply a constant charge, then they will come closer. Do you see this? If you keep Q fixed somehow, then in order to reduce your energy, you have to increase your capacitance. And in order to increase capacitance, you have to decrease your distance between the copper plates. So in case of a fixed charge, these two plates will come closer. In the case of having a fixed voltage, these two plates will go farther away from each other. Is it getting too complex? No? I'm sorry if I make it a little bit complex, but the case that I want to point out is that when we decide about whether it reduces the energy or not, you always look into whether changing one parameter also impacts the other parameter. All right? For this case, the change of D would change Q, the charge, but it will not change the voltage V. This is why it's safer if you start with these equations. But if you could somehow keep the charge fixed, then this guy would come closer. In this case, I will use the other equations. Although they are numerically same, but their implication is different because one of them is going to be changing and depending on the other parameters. All right. Okay then. So we spoke a little bit today. Tomorrow we'll have an exam based on whatever we discussed, and get prepared for your midterm exam. And in the previous exam, I saw that some of your grades was not like maybe was not that great. And what surprised me is that not all the people did very bad in the quiz, but in the exam their grade was very low for some reason. So I mean it was a shock for me, because typically people who do good in the class quiz also tend to do good in the midterm exam. So I'm not sure that what's, I mean, so I want to hear from you guys, like what actually caused this discrepancy. For only people who didn't have, yes, go ahead.
For one question, that was worth 10 points.
For one question, 10 points, okay. So that question was also covered in the class, right? So I discussed a similar problem in the class. Actually, in the class, we discussed a problem which is far more difficult, actually. We had wires in one direction and wires in other directions, and then we solved this problem. So, so I think it's not a very good excuse that one question could carry huge weightage, because guys, you are growing up. I mean, if I give you simpler questions in the exam compared to what I discussed in the class, maybe you should change your strategy. That maybe something has to be done on your side. So in this midterm exam, I'll try to introduce some more segmentation of the questions. So maybe instead of having a big chunk, maybe I will bring it down a little bit, chunk it down. But please be extra cautious so that you do not lose unnecessary marks. Okay. And in the theory, I guess it will more or less will be similar to whatever we encounter in our class quiz. We'll have similar kind of theory in the exam as and the math will be more or less whatever you covered in the homework, and that's all. Yeah. So just stick to your class notes. Go over it over and over and over, please. We still have 10 more days to go, more than 10 days to go. And I believe that if you take care of it, you should be fine. Even if your midterm exam, first midterm exam was not that good, it should be all right if you can pull it up this time. All right. Does it answer your question? Okay. Okay. So does it address your opinion?
Yeah.
Okay. Okay. Thank you.
Will we be getting the, I think we discussed this after the first exam, but will you be giving us the additional 15 minutes?
Oh, yes. Yes.
Okay.
I said it. So it will be full 1 hour and 15 minutes.
Okay. Thank you.
For the project, how do we know if we're right for our simulations? We have to like show you it, or I don't really know how to compare it to if it's correct or not.
Oh, don't worry about the calibration. So you're talking about the calibration, like whether it is correct or not.
Yeah.
Don't worry about the corrections. As long as it matches with your intuitions, let's say that you put some charges and you see that the other test charge is going in the right directions, I think it's fine.
Okay.
Okay. Yeah, this is also other good point. Have you guys started to work on this project?
A little bit.
Little bit? Very good. So whatever you have, you don't have to go to the very entire last point, because the initial part is easier. As you go to the next part, it becomes a little bit more difficult. So it doesn't mean that you have to complete all these 5 different problems. Even if you've done a few steps, like 2 or 3, I think it should be fine. It will give you a good beginning. Okay? So take full advantage of that. All right, guys. Thank you so much for your time. Hope to see you.